We're live. Welcome everyone to another Unicorn seminar, and we're very delighted to welcome today's talk by John Teufel. But before we get to that, there's a few announcements. So if I just pass over to Sophia, if you want to just announce the poster sessions.
Yeah, thanks, Madassa. So another reminder that Unicorn is organizing a poster session. So this is going to take place on the 16th and 23rd of June. We'll have poster prizes and a jury made up of people from journals and EPSRC. And we really want to provide the space for people to just socialize and network after 1 year of virtual seminars. So please sign up. We'll put this sign up link in the chat in a moment. And we look forward to seeing you.
Thank you.
Back to you, Madassa.
Next page, if that's okay. So just before we start off, let me remind you of the block we're in. Of course, we're focusing this block towards quantum state control and preparation. There's 2 additional sessions to happen in the following 3 weeks. And just as a precursor to that, so next week, of course, we'll focus on the early career researchers, and they'll be giving talks. Oh, I think you've lost the screen for that. We'll be joined by John Price, Clara Ventura, and Ricardo Antunes. So keep that in your diaries, please. So for today, I'm very delighted to welcome Edward Led. He's a lecturer in experimental condensed matter physics at Lancaster University, and is also a member of BORN, that's the British Optomechanics Research Network. Edward, following his undergraduate degree at Oxford, went to do a PhD at Harvard in spin qubits and semiconductor quantum dots in the group of Charles Marcus. He then did various positions at Delft, University of Technology, as well as University of Oxford. And then in 2018, started his own group in Lancaster, moved to Lancaster, sorry. And his focus is quantum electronics and nanoscale devices. So I'm delighted to have him chair today's talk. So without further ado, Edward, the floor is yours.
Good. Thank you very much, Madassa. So I am very happy to be chairing this session by John Teufel. So John's work on micromechanics and optomechanics has been inspiring me as long as I have been working in this field. So let me tell you John's biography. He's an experimental physicist at the National Institute of Science and Technology in Boulder, Colorado. He did his PhD in physics in Yale, and after that he began research on microwave optomechanical circuits as a postdoctoral researcher at GILA, which is a joint institute between the University of Colorado and NIST. He's now part of the Advanced Microwave Photonics group at NIST. He has pioneered efforts in engineering superconducting microwave circuits to experimentally explore the role of quantum mechanics in macroscopic mechanical systems. He combines the tools of nanolithography, cryogenic measurements, and microwave quantum optics, which means it's now possible to fabricate circuits in which radiation pressure forces from microwave photons can be used to control and measure mechanical motion at the quantum level. In addition to fundamental science, this research is driven by applications related to quantum information processing, precision measurement, and quantum-enhanced sensing. In 2017, John was awarded the Presidential Early Career Award for Scientists and Engineers for his innovations in quantum optomechanics that are helping mechanical technologies approach the quantum limits. And I think that's what he's going to be talking about today. So fresh out of last week's Science, an article on deterministic entangling mechanical motion, John is going to talk about listening to quantum entanglement.
Great.
Thank you, John.
Thank you for the introduction. Let me see if I can go ahead and share my screen. Let's see, just to check that the screen is sharing okay, if somebody can alert me if it's not, but otherwise I'll go ahead. First I want to thank the organizers for giving me the opportunity to talk about our research, and it's always exciting also to talk about research that's fresh off the presses, as we said. So the title of my talk is Listening to the Sound of Quantum Entanglement. And as you heard in the introduction, my goals in life are to really see what we can do in the lab to engineer the ability to prepare and measure quantumness of macroscopic systems and specifically mechanical systems. The artist rendition you see here on my title slide was our attempt to try to convey what entanglement might look like, and also why it's very elusive to see or image. The ideas we had in the back of their mind came from more of a philosophy background, the idea of the allegory of the cave from Plato, that no matter what you do, you see the shadows can let you infer what's going on, but our goals are to disentangle, if you will, what's going on at the quantum level. If you don't like all that, when I showed this picture to my 13-year-old son, he said, I don't get it, but I guess it's kind of cool. And so that's about the nicest thing he's ever said to me, so I will take it. So as I mentioned, let's see if my pointer is working. Give me 1 second. What I'm going to be talking about today is recent work that came out in Science, where we set out with the goal to deterministically entangle and do complete tomography of two mechanical modes in an entangled state. And so that's what I'm going to tell you about today. Over the past week and a half since it came out, there's been some media attention. I found this funny. I thought I would share some of these things got passed around on Reddit, and as Reddit is good for, it's good for quick blurbs and things, and then lots of comments on random people trying to explain your work. Some of my favorite comments that I saw were from Ben Rosen. Do you guys just put the word quantum in front of everything? I think that's a valid question. What I like even better is the very valid answer given by Big Mike 420, who said quantum yes. So with this, I will talk about some of our quantum experiments that hopefully what we're doing is more than just sprinkling the word quantum in front of what we usually do. So the big picture, what I'm going to talk about is give a brief introduction to optomechanics. I realize this is primarily an optomechanics seminar, so there's some background. I'll go quickly, mostly to set the notation and the variables and the important figures of merits in my own terms, and hopefully compare back and forth traditional optomechanics with what I'll call circuit optomechanics or microwave optomechanics. The idea where your electromagnetic mode is not a Fabry-Perot with a laser, but superconducting microwave circuits. I'll then go through our recent experiments on entanglement, and then with the last few minutes of the talk, I'll tell you what we're up to now, what we're pushing towards, some of the larger goals that I think are very much in line with the goals of this seminar, pushing towards full arbitrary quantum control and measurement of motional states. Just as a broad scope, again, my primary appointment is at NIST. I work in the Advanced Microwave Photonics group. It's a number of students, postdocs, but also PIs, where we work on a number of different topics. A large portion of the group is superconducting qubits with Josephson junction technology. We also develop Josephson junction technology to make things like quantum limited amplifiers. These parametric amplifiers are very much like optical parametric amplifiers. You can use them as sources of squeezed microwave light, or phase sensitive amplifiers or phase insensitive amplifiers that approach quantum limits. And the last kind of third of the group is what I will call the quantum mechanics. And these are these mechanically compliant circuits that I'll focus on mostly in this talk. So again, what I'm going to talk about over and over are what I show in this false color SEM picture. This is one of our devices. Our bread and butter is to measure these drum resonators, and you can really think of it as vibrating like a circular membrane. And the whole idea is that this flimsy top plate of aluminum, let's see if I can get a pointer on here. This top plate of aluminum is suspended over about a 20 micron diameter, and so you have a membrane that's free to vibrate in this megahertz regime. Now we pattern this as a vacuum gap capacitor, so as it vibrates, we can measure it very well. And this is our quantum object of interest. This has been our bread and butter. But just to say what we're interested in, why mechanics and what we like about them, what is good about them. From a quantum technology perspective, what is nice is not just that it's a high Q resonator, but it's compact. It has large dynamic range. For better or for worse, it's very linear. So we can do things at the quantum level, but we can also do things at the billions or even more quanta level. And these are tools that are not just useful, but crucial in many of the quantum applications. Just to set the scale, when I say compact, what you can compare to is what would a 20 megahertz electrical resonator look like? Here's a picture from CERN, and this is just a visual representation about the very different wavelengths involved between the speed of sound or the speed of light. Now, of course, you can make much more compact electrical resonators, but in your mind, you should think of these as both kind of roughly circular modes working near the fundamental. One of the things that's particularly great about these mechanical oscillators, and specifically what you have access to with cavity optomechanics, is the idea that cavity optomechanics gives you parametric coupling. The ability to, when you want to talk to the mechanics, you can by using radiation pressure forces. And the idea of what we have is mechanics that's very long-lived, natural lifetimes that ring down on the order of milliseconds or even seconds now in state-of-the-art devices. But at your will, you can apply control pulses with the photons that takes this line width from the hertz scale to the megahertz scale. And again, this kind of dynamic range that you have is part of what makes it useful as a tool. So again, to begin at the beginning, if you have a mechanical degree of freedom and you were to ask, how do you measure it in the first place? How do you measure it at the quantum scale, which again, for these devices means measuring at the 0-point motion, which for engineered mechanical systems is of order femtometer, the diameter of maybe a nuclear distance. So if you have a boundary condition, you want to measure where it is, the simplest thing you can do is bounce a laser off of it. And if you look at what comes back, if the path length is moving back and forth at some mechanical frequency, well, that will phase modulate your light. And in the frequency domain, you will acquire phase modulation sidebands. Now, of course, you can do much better than just bouncing off a simply boundary condition. You can add another boundary condition, and you can make a resonant enhancement. The way I like to think about what a Fabry-Perot cavity would do is you now boost up the number of photons in the cavity by a factor of Q. You've now steepened your transduction slope also by a similar factor. So now for every little bit of motion, you get more interaction with a given photon, and you've enhanced the interaction, giving yourself both better ways to measure this motion and also to impart radiation pressure forces. And these will go hand in hand, as you will hear throughout the talk. Now, what I want to push to is a Fabry-Perot cavity with a movable mirror. In a circuit language, what you could also think of is an inductor capacitor circuit with a mechanically compliant circuit element, either a mechanically compliant inductor or capacitor. The version that we use in our lab is this mechanically compliant capacitor. So as it vibrates up and down, it modulates the capacitance, which modulates the resonant frequency of an electromagnetic resonator. And the physics is very, very similar. Highly analogous to exactly what you would get for solving electromagnetic waves in a Fabry-Perot. So again, for all of these devices, you have a zoo of optomechanical systems that we've all seen and heard. Everything from LIGO at the large scale down to clouds of cold atoms at the very nanoscale. All of these are described by the optomechanical Hamiltonian. I won't go into too much detail, as I assume you've heard it before. But what you have is the photons, the A dagger A's, interacting with the phonons, the B dagger B's in the system. What you have on the right, the 0-point motion of the B dagger plus B, that is just the displacement of the mechanical harmonic oscillator. And again, it's set by the 0-point scale, which, just to point out, for these relatively massive systems, again, when I say massive, I mean compared to something like a trapped ion, this 0-point scale is on the femtometer scale instead of the nanometer scale like that of atomic systems. So if what's on the right is a position, what's on the left must by definition be the force. And this is in fact the radiation pressure force. And the fundamental constant there is just making a cavity, an electromagnetic cavity, that is as mechanically compliant as possible, that has the biggest transduction factor of how much the frequency of that cavity shifts per unit motion. Now, in the end, it doesn't do us any good to optimize this derivative, this d omega dx, or the 0-point motion alone, What we really care about is the product, and that gives us a vacuum coupling rate. And this is also highly analogous to cavity QED or even circuit QED, where you have a dimensionless a real coupling rate between two harmonic oscillators in the system. And what I want to point out here, the nonlinearity is in the coupling. You have a beautifully harmonic oscillator in the cavity, a very linear harmonic oscillator in the mechanics, and this coupling rate has access to nonlinear phenomena in principle. As I said, I will constantly touch base with the Fabry-Pro cavity with a movable mirror. I think that's kind of the standard that we all know how to think about, and highlight over and over what I'm going to do in this talk looks really as simple as this. It's just an LC resonant circuit. We can couple to the outside world. Instead of making a transmissivity of a mirror, we can choose to capacitively or inductively couple to the outside world to 50 ohm coax cables or amplifiers or measurement apparatus with whatever strength we would like. And again, the physics is exactly the same. So how do I think about this vacuum coupling rate that I told you is so important? What sets this rate? Well, in a canonical Fabry-Perot cavity, it's a very, very simple formula. This vacuum coupling rate of how these two harmonic oscillators interact, the overall frequency scale is set by the frequency of the cavity. So in the optical domain, you're talking about 200 terahertz. And then you have this ratio of length scales, the ratio of the 0-point motion to essentially the one-dimensional mode volume of your cavity, or more specifically, just the length of your cavity. Now, this ratio is very small because this is something like femtometers to hundreds of nanometers at best. But overall, you can get very high coupling rates. In the microwave, again, what's crucial here is you're not thinking about a distributed resonator, a lambda over 2 or lambda over 4 or 10 lambda resonator. It's an LC resonant circuit. So for better or for worse, what we have access to in the microwave regime is lumped elements. And the beauty of that is the characteristic length scale in the problem is now the plates between the capacitors. So if I were to think about the G naught, again, the frequency scale is set by the frequency of the cavity. For us, it's going to be around 10 gigahertz or so. So unfortunately, that means we're taking a factor of 10,000 hit compared to optical systems. But where we can win it back is again in this length scale. Because these are lump circuit elements, we can engineer this length scale to be tens of nanometers, very, very sub wavelength, which again is good because our wavelengths here are order centimeters. Now, the thing I've left off of this problem is there's one last thing that I'll call the participation ratio. Ideally, what you want is the only capacitor in the system to be the mechanically compliant one. If there's other parasitics capacitance in the circuit, well, that will divide down this participation ratio. But what's nice about the circuits that we make is to a very good approximation, the only capacitor is our drum vibrating up and down, resonating with a superconducting spiral inductor that gives us a very high Q electromagnetic mode. And again, this vacuum coupling rate, while I spend most of my career trying to engineer that to be bigger and bigger, in the end, it's still not big enough. That's an active area of research. But as we know in love and optomechanics, you're not stuck with the vacuum coupling rate. If you were to pump the cavity with a coherent state, in other words, displace the cavity mode far from the origin, you can parametrically enhance your coupling rate to get an effective G that scales as the square root of number of photons in the cavity. And again, here's why it's important for quantum technology that the cavity is in fact linear. The fact that we're able to pump it with millions or billions of photons allows us to get this parametrically tunable coupling rate, again, from completely negligible up to megahertz coupling rates. So how do I think about the quantum harmonic oscillator? Again, the idea that we have in mind is you have some mechanical mode. For better or worse, it's coupled to some thermal acoustic environment. And that thermal environment, to a good approximation, we're in the Rayleigh-Jeans limit here, where KT is bigger than the frequency of motion. Again, the frequencies we're talking about is maybe a 10 megahertz mechanical mode. And even though we're going to put this in dilution refrigerators, put it in the coldest cryostats you can buy, the thermal motion is still not going to be naturally in its ground state. So it acquires its equilibrium occupancy through some intrinsic coupling to the bath, through whatever intrinsic loss it has. Now, the idea of cavity optomechanics is to be able to do something with this. But in order to do something with this, you need to have the right parameters in the first place. One of the things I'll point out for thinking about mechanical oscillators as a quantum technology, it's not the natural Q or ring down time of the mechanics that's most important. It's the fact that it's coupled to a hot bath. So just like a trapped ion, the dominant decoherence mechanism is a thermal decoherence rate. And that's this product of the bath occupancy times the coupling rate to that bath. For the devices we're going to talk about, we can make that thermal decoherence rate very low so that we can overwhelm it with good rates. As you may have heard in other seminars, people are working hard to make this thermal decoherence rate, in fact, so small that you can imagine doing quantum things even without cryogenics. Just do it naturally at room temperature. And this is what I highlight as the quantum-abled regime. You need to at least have a mechanical frequency that's vibrating fast enough so that if you were to cool it and DQ it, it could still be a harmonic mode when you're in its ground state. So that's what I'll refer to as the quantum-enabled regime. And this is what you would need to do, say, cooling to the ground state, or just the simplest possible kind of quantum state preparation. And that goes for sideband cooling or active cooling. So as I said, this thermal decoherence rate or this thermal decoherence time, it doesn't care about the occupancy of the bath or the coupling, but really the product of the two. And what's interesting is in this Rayleigh-Jeans regime, the mechanical frequency actually falls out. And the figure of merit solely cares about the temperature of the bath and the Q of the mechanical oscillator. So just to set the scale, for a sort of millisecond coherence time, something that would be a very, very useful quantum technology, well, you can use a higher Q mechanical system and have the freedom to operate at higher temperatures. So what I have in mind is, for example, levitated nanospheres. They're much like trapped ions in that they're not physically connected to anything. The intrinsic quality factor can be billions or tens of billions. And even if you're coupled to an ambient bath, you're talking about intrinsic millisecond coherence time. Likewise, you can do things like I believe you heard about recently in the Schlieser group. You can take these soft clamped membranes, these silicon nitride membranes that are high tension, that are engineered with phononic band gaps, and you can get Qs of order a billion, and you can also operate them at about 10 Kelvin, and you can get that same millisecond coherence time. For our devices, I apologize, we only have a Q of a million these days. I assure you we're working on it. But I like being in a field where I have to apologize for a Q of a million. I think this just shows a lot of the potential of these mechanical systems. But the pro and the con is, one, you could say, well, they have to work cryogenically. But I would say back to you is, but we get to work cryogenically. And for every quantum optomechanics experiment, being able to start at a colder temperature, it always helps. It always sets a different scale or a better scale for your thermodecoherence rate, which is the dominant mechanism in these systems. And again, that's another advantage of using microwave photons over the optical photons. Yes, each photon has 10,000 times less energy, but it means if I were to illuminate my drum with nanobots of microwave power, that's an unbelievable number of photons per second. Again, that same factor of 10,000 times more than the same optical power. So now on to cavity optomechanics. I have a mechanical mode. As I said, you're going to couple it to some cavity mode, which is also coupled to a bath through some hopefully overcoupled engineered decoherence. You've coupled a kappa to an environment that is your measurement infrastructure. And what's nice is both for optics at room temperature or microwaves at dilution refrigerator temperatures, you can essentially assume your cavity is in a cold state. In the so-called weak coupling regime, where this parametric coupling G is much less than the cavity decoherence rate, effectively from the perspective of the mechanics, what it sees is a detailed balance or a rate equation. It sees a heating rate coming from the bath of mechanical quanta trying to come into the system and drive it to equilibrium in thermal. But then you can couple it with a beam splitter Hamiltonian to the cavity, which quickly decays into its cold environment. So you see a cooling rate, this 4G squared over kappa. And this should look very familiar, again, from a kind of a dispersive coupling approximation from cavity QED, if you've seen things like that. The figure of merit in these things is the ratio of the good rates to the bad rates. One way to quantify that, again, is using a cooperativity. And throughout this talk, I'll refer to a quantum cooperativity, just meaning I'm going to measure the normalized coupling as compared to the dissipations or decoherences of the system. For the cavity, that's the rate cavity, the rate kappa. And for the mechanics, it's this thermal heating rate. And this quantum cooperativity, this is what you want to make as large as possible to have access to all the beautiful quantum state preparations and measurements that the field is most excited about. So that is the weak coupling regime, where this coupling you can think of as small. It's trying to take mechanical quanta and put it in the cavity, and then it immediately leaves out of the cavity. What would happen if you turn up your coupling rate even faster? Well, what you can get is something like a vacuum Rabi rate, where the mechanics is undergoing a beam splitter interaction with the cavity. And so mechanical quanta go to the cavity, but then before they can leak to the cavity, they actually cycle back and forth and back and forth. And again, this is the strong coupling regime. This is what you'd like, ideally, to have most access to do whatever you want. And in this sense, you could do things like ground state cooling. Instead of just leaving your cooling on as a steady state, you could do things like more swap the hot state of the mechanics to the cavity and then turn off your coupling. And again, this is the desired hierarchy of rates. You want your thermal decoherence rate to be lowest, then you need kappa to be bigger in order to have some cooling. And ideally, you'd like to be able to make G as big as you can. And again, for these systems, if G were to approach the mechanical resonant frequency, you can actually run into ultra strong coupling effects. These are things I won't talk about, but we do have papers on really pushing the limits where we can get coupling constants of order 10 megahertz, which is of order the mechanical resonant frequency. So how should I think about this in a quantum optics terminology? So what I'm going to show you throughout this talk is really get used to thinking about the phase space distribution of the harmonic oscillators. And again, the two harmonic oscillators you have are a phase space distribution of your cold cavity, that's essentially in its ground state, and a hot mechanics that's maybe in our devices starting with 20 to 50 quanta in it or so. If you were to turn on this beam splitter interaction by pumping optimally red detuned, by pumping below the cavity by a mechanical resonant frequency in the resolved sideband regime, so I can ignore this Stokes process that's also always there at some level, what you would see if I were to play a movie for this phase space distribution is, again, just Rabi flopping. You send back and forth in the time domain, the state of the mechanics and the state of the cavity. Now, some things that I will point out is unlike the James-Cummings Hamiltonian, which couples a two-level system to a cavity, this swap is independent to the number of quanta in your harmonic oscillator. In fact, if you had 1 million quanta in your mode, you could swap 1 million quanta. If you had a cat state or a fancy GKP state, you could swap that whole state at once without having to individually tailor it photon by photon. Now, the title of this slide is the beam splitter without loss, where I now have shown you this ideal conservative system where nothing goes anywhere. You just swap back and forth. And the idea I want you to make sure you know is without loss, there can be no cooling. You have a closed system, so that energy is just being sent back and forth, but never really leaving the system. Luckily, in our systems, like all systems, there is loss. And now if you think about this strong coupling regime in the presence of loss, well, yes, you swap the state back and forth, but also the total entropy of the system is decaying. And in the end, what you realize is you use your cold cavity as your pure resource state to initialize a pure state of the mechanics as well. Now, that was the beam splitter interaction, but what I want to get to for the ideas of entanglement is that you can do the same parametric coupling, but instead of pumping the red sideband, you can pump the blue sideband. And again, if you make a good cavity approximation, where the cavity line with kappa is much narrower than your mechanical resonant frequency, the Hamiltonian that results is the two-mode squeezing Hamiltonian. Again, this is the A dagger, B dagger interaction. So the idea is instead of swapping photons and phonons, you're going to create beautifully correlated photon-phonon pairs. And of course, the conjugate is correlated annihilation of photon-phonon pairs. And this sort of process is not energy conserving. But if you weren't to think about it, you can still use a rate equation, a detailed balance. You still have your thermal heating rate, but now you get this negative damping rate, which again, I want you to think about as Negative damping means your exponentials are not decaying, they're increasing. So you should think about it in its mind, maybe cartoonishly as heating, but more rigorously as exponential growth or amplification. So again, if we go back to these phase-space distributions, if you start with a cold cavity and a hot mechanical system, and you turn on a two-mode squeezing interaction, what you see in phase spaces both grow exponentially. And this is just the physics of the two-mode squeezing Hamiltonian. And if you watch in the time domain, you get, pardon me, the cinches and the cauches that you expect exactly from a quantum optics textbook. And the way you should think about it is the cold cavity is the idler of the mechanics, or the hot mechanics is the idler of the cavity. But you have this intrinsic two-mode squeeze system. And this is the photon-phonon entanglement that grows exponentially in time. And if all is right in the universe, you're doing your entanglement much faster than your decoherence rates, this thermal heating rate. You can be initialized in very pure entangled states. Again, this is a way to get entangled photons entangled with phonons in the mechanics. So that's the finished part of my cartoon introduction in the theory. Again, looking at the devices, this is an SEM picture of one of our devices. Just to call out the leg scales, again, you're talking about drums that are maybe 10 or 20 microns in diameter. You hover a top plate of the capacitor, maybe 10 or 20 nanometers above the other plate. This tens of femtofarad capacitor is resonating with a spiral inductor made out of superconducting aluminum. So it's essentially lossless is the way you should think about it, to a good approximation. And what you get here is then an LC resonant circuit in the microwave regime that you can talk to electromagnetically. If anybody's interested, I'm always happy to talk about the details of the fab. But again, in our finished chip, essentially we just have a sapphire substrate, a bottom layer of aluminum. There's a sacrificial layer that we completely removed, and then another top layer of aluminum. So if we've done everything right in our process, the only atoms that are here are aluminum and oxygen that make up either the metal or the sapphire substrate. These circuits have been very good to us. I won't go into detail. These are some of the first devices ever to demonstrate sideband cooling in optomechanics to the ground state. But you could also do things like quantum state transfer or initialized squeeze states. We are NIST, so we also push very hard on understanding and demonstrating the quantum limits of measurement. And these things are very naturally, because of their high Q and their low temperatures and their good measurement sensitivity, very good force sensors, again, at the atto-Newton per root hertz level, or displacement sensors at the attometer per root hertz level. With these microwave circuits, we also do things pushing towards microwave networking or quantum networking, the idea that you can take a mechanical element and couple it to multiple cavities in order to do things like quantum frequency conversion, to send in photons at 5 gigahertz, swap them into the mechanics, and swap them back out at, say, 8 gigahertz, for example. And these are things you can do reciprocally or even engineer non-reciprocity at the quantum level, meaning with minimal atom noise and high efficiency. And some of the last things that we've been pushing on over the past few years is using quantum enhanced sensing, or the idea of not illuminating just with coherent states of the microwave field, but more interesting states, specifically like squeeze states of the microwave field, which, as I said, we separate in other parts, we generate in other parts of our lab with things like our Josephson parametric amplifiers. So looking at illuminating these optomechanical circuits with squeeze states demonstrated you can do things like better measurements or even surprisingly better sideband cooling. Now, the heart of the talk today that I'm going to get to is about entanglement. Why it's useful as a quantum technology? Well, it's the backbone of things like communication and teleportation and quantum enhanced sensing. But again, why it's hard? Well, you have the quantum conundrum. You need two elements that are as isolated from everything in the universe when you want, but then when you want, they need to be able to strongly talk to each other, but no one else. That's the idea of entanglement. And then you need to be able to measure, so they need to talk to you and no one else. And here's the cartoon picture of, say, trying to measure two pendula by doing the equivalent of Doppler radar. Maybe send some microwave pulses to know where they are, or microwave pulses to make these things interact. So here's our idea. We're going to engineer a single electromagnetic cavity, and we're going to put 2 mechanical degrees of freedom. I've told you about our building blocks. We have access to beam splitter interactions and 2-mode squeezing interactions. And what you can think about is kind of a bucket brigade way to do this is, what if I do a 2-mode squeezing pulse between drum 1 in the cavity? I now made a photon-phonon pair. And then I do a beam splitter pulse to swap that photon into a phonon of drum 2. That would be one method conceptually to now make an entangled phonon-phonon pair. That works, but what is tricky about that is if you have cavity loss, now the ability to do these kind of pi pulse entangle and swap interactions really hurts your fidelity. Luckily, there's many protocols where you can use that as the right cartoon idea, but instead of doing sequentially, actually apply simultaneously a 2-mode squeezing interaction between drum 1 in the cavity and a beam splitter interaction between drum 2 in the cavity. And surprisingly, despite the fact that the cavity is always radiating information, and the fact that you basically have a tripartite system, the surprising part is that you can get very clean entanglement bipartite between the 2 drums tracing over the cavity. And that it's not at all obvious, but that's what we will take advantage of in our experiments. Now, just to give a little bit of history about what's done, for me, as I've referred to, I have a lot of reverence for the trapped ion community. In my mind, they did everything back in the 80s and early 90s. But surprisingly, entangling the motion of 2 independent trapped ions was only done about a decade ago. And in our field of cavity optomechanics, there was seminal work, both by the Alto group, the Grobacher group, showing the first demonstrations of entanglement, mechanical entanglement. Part of our goals were to set out and get all the pros of all these systems. Make your entanglement deterministically on demand, do it in continuous variables, so you really have access to the full Hilbert space of your linear harmonic oscillator, and do a high quality, efficient measurement and tomography of the system. So here's what our device looks like. Again, what we're going to do is we're going to take an inductor capacitor circuit where now there's 2 capacitors, there's 2 drums. We're going to send microwaves in, interact with the drums, and look at what comes out. Here are 2 mechanical modes. I won't go into detail. What you can see is we've made them these oblong shaped, basically so we can access the 1-1 mode of one drum and the other 1-1 mode of the other drum. And this lets us really know which drum is which. And the whole idea is to entangle the motion of this drum with the motion of this drum, deterministically and unambiguously. I want to note that while they are connected by electrode, these 2 mechanical drums don't talk to each other mechanically. I guess in principle, this motion could radiate out into the substrate and vibrations could couple to the other mode. But as I said, these are high Q mechanical oscillators, the Q of order 1,000,000. And the modes that we're talking about are millions of line widths detuned. For example, this mode is at about 10 megahertz. This mode's at about 15 megahertz, many, many, many line widths away. So how do you measure this motion? And what we're going to do is the analog of homodyne or heterodyne measurements in the microwave regime. That means illuminate with a coherent state, couple that into our overcoupled 1-port cavity, which is an LC resonant circuit, and look at what comes back by amplifying with the lowest noise amplifiers and demodulating however we'd like at room temperature. Now, unfortunately, even the best cryogenic Hemp amplifiers are far from quantum limited. In terms of quantum optics, you can think of them as having an effective efficiency of something like 1%. For every 1 signal photon, you have about 100 noise photons, just as a rough order of magnitude. Now, the solution, what we and many other groups do, is actually insert preamplifiers. Insert Josephson parametric amplifiers as a preamplifier that's your lowest noise amplifier that can give you, in principle, arbitrarily high, either homodyne or heterodyne effective efficiency in these circuits. And these are devices we fab and use all the time at NIST, both for our qubit experiments and for some of our optomechanics. And they're tunable things where essentially it's a squid circuit as your nonlinear element. You can tune it on resonant with the cavity. You can pump it and use parametric gain to get, again, phase sensitive or insensitive gain. Now, unfortunately, there's a problem in the compatibility between optomechanics. and the JPA circuits. And that is just the dynamic range. As I told you, we're going to pump the optomechanics with millions of photons, and that would be enough to completely obliterate or saturate the signal into JPA. So what we have to do is inject a cancellation tone, which is technically feasible, but annoying and technically challenging. As the advisor, it's not so bad. For the student or postdoc that has to do it, you can lose a lot of time and effort. What we're going to do in this experiment is actually a bit of a clever trick. We're going to use the optomechanical circuit as its own parametric amplifier. As I told you, the two-mode squeezing interaction is in fact an amplification process. So in the measurements I'm going to show you, we achieve very high measurement efficiency with traditional Hempt amplifiers, even though we never use a JPA. So this is what the experiment looks like. Again, if you were to put it in a dilution refrigerator, most of what you see is gold-plated components and coaxial cables. This is our sample box. This is the single port to which it's coupled, in which we'll inject our microwave control signals and listen to what comes out. Now, our protocol for the entanglement measurement is going to be as follows. You're going to apply one pulse to cool both drums. You're going to apply another pulse, again, a red and a blue pulse simultaneously to do your entanglement. Then we're going to apply a blue pulse to do our readout, to do our phase insensitive amplification simultaneously of the two mechanical modes. And then we'll institute a reset protocol. We're going to do this over and over. And the idea is after each run of the protocol, we will measure the 4 variables of our two-mode mechanical system, i.e. the position and momentum of drum 1 and the position and momentum of drum 2. And in every shot, we will simultaneously acquire all 4 of these variables. We can then do this over and over and get the statistics, and that is going to be our entanglement witness. So in principle, these ideas have been used before, but I just want to say kind of doing the combination of frequency and time domain multiplexing to get everything working at once. This was a lot of work and a lot of the time that went into this experiment. So again, here's our protocol. We have our 2 drums interacting with the resonant circuit. We do a cooling pulse for drum 1 and drum 2, and it's short entanglement pulse, and then a strong readout pulse at the output. So what does entanglement look like in theory? Again, I'll go back to these same phase-based distributions. You should think of this as position and momentum of the mechanical oscillator 1 and 2, and these are the resulting histograms in the X or P directions. Now, if you turn on the entanglement, you start in a cold state, because that's where we initialized. And from the perspective of drum 1, he just looks like he got high. Or the perspective of drum 2, he looks like he got high. But the interesting part is not the individual distributions, but really looking at the cross correlations, looking at the position of drum 1 as a function of position of drum 2. And these highly elliptical cross correlations are exactly the hallmarks of entanglement. This is saying that these are not independent hot modes, but that if drum 1 is far from its equilibrium position, drum 2 is also with high certainty. And this is, in fact, the definition of your two-mode squeezing interaction. Now, when we go into the lab and we measure the distributions, these are, in fact, exactly what we see. These are the snapshots of our entanglement tomography. Again, what I want to point out is that we're able to initialize very close to the ground state in the beginning. We're able to do a very high fidelity measurement, adding very close to the minimum added noise allowed by quantum mechanics for simultaneous measurements of variables. And what we can clearly see is this elliptical nature evolving in the cross correlations. So that's the smoking gun of entanglement. And I just want to say that this is our tomography, again, that we have of our fully cold state. You can think of knowing the entire density matrix of the system, or now you have our highly correlated state. And then if you look in the density matrix formalism, the hallmark is these strong off-diagonal elements. And again, if I call note to the size scale, this is a much more energetic state, but it's these off-diagonal elements that are what we're after. So what does the entanglement look, what does the energy look like versus time? Well, again, if you just had a blue pulse on, you would have exponential growth. A red pulse on would be decay. When you have them on simultaneously, what you can already see just in the energy of drum 1 and drum 2 is neither are growing exponentially. You have this polynomial growth, exactly in agreement with theory. Now I keep referring to these things as smoking guns. You have energy growing. You see an ellipse. In fact, we can even fit the angle of this ellipse, and we can see that it agrees well with theory in the angle. But the real proof in the pudding is the Dwan-Simon criteria. And this is a way, if you have access to the full density matrix, access to all 4 variables of your system, what you can do is look at the partial transpose and take the partial transpose of the covariance matrix and look at the minimum symplectic eigenvalue. That's a whole lot of words. Blech. What does it mean? It means if you were to look essentially at the waist of the ellipse in the narrowest direction, this is a procedure to find the eigenvector and the eigenvalue. And if it's below a half, again, half just being vacuum in the units that we've chose, then you have an entangled state that can be not be explained by classical physics. So what does our data look like? Our data looks like this. This is our minimum symplectic eigenvalue as a function of the measurement, the entanglement time. You can see we start not perfectly in the ground state. So for a little bit of time, we're approaching the 1/2 threshold, and then we go below it. And what we're most excited about is that we go visibly below it without subtracting variables or doing tricky analysis. This is taking the raw output histograms and analyzing them properly. You can see we clearly violate the entanglement threshold. Now, we also are able to characterize the efficiency of our measurement, or I should say the infidelity due to our not 100% perfect measurement. And if we were to ask the separate question of what is the inferred state that we originally had, what we're seeing is we're making a 2-mode squeeze state between the mechanics of about 4 dB below vacuum, or 4 dB below the separability criterion. And what we worked a lot with our theory collaborators is not just this entanglement, but really putting the error bars. And this was done with parametric bootstrapping. And this was part of the work of our colleagues of Manny Nill and Scott Glancy, also at NIST. So with the last maybe 2 minutes of my talk, I just want to go through some of our future directions. One of the things I will highlight as a field, much of the excitement is in quantum computing and towards the goals of quantum supremacy, taking engineered quantum systems and doing things that you couldn't do with classical computers. One of the primary ways to do that in the field is to take many, many 2-level systems, many, many qubits, and you need ideally maybe hundreds of thousands of millions of them so that you can do error correction, so that you can take imperfect qubits and turn them into fault-tolerant logical qubits. Now, another approach is actually to use the very large Hilbert space of harmonic oscillators to encode your quantum information. And you still use 2-level systems like a transmon as your nonlinear resource, but the idea is your quantum state is now encoded in the harmonic oscillator. And these are things that are like binomial codes or CAT codes or GKP states are an active area of research, both in circuit, QED, or the trapped ion community, or many others. This is just a way to say the full quantum control over long-lived harmonic oscillators is a path towards scaling quantum technology. Now, all these beautiful measurements I've showed you about optomechanics thus far, they're great, but they're Gaussian. And they're Gaussian because we've linearized our Hamiltonian. Our beautiful non-Gaussian resource that we have access to in the microwave is just essentially the Josephson technology, the superconducting qubits. They can be single photon sources. They can make squeeze states, CAT states, arbitrary Fock states, entangled states, whatever fancy state you want, again, because of the nonlinearity of the Joseph junction. Unfortunately, with our standard optomechanical devices and our parameters and our G naughts that I'm very proud of, well, you still have to pump with these maybe 10,000 photons to get to quantum cooperativity of 1, or maybe 1 million photons to get to strong coupling. And just like with our parametric amplifiers, that's highly incompatible with the quantum circuits, with 2-level systems or qubits that are nonlinear by definition at the single photon level. We work towards devices, even maybe 5 or 6 years ago, we can fabricate circuits that have qubits and drums on them. And you can do things like use time domain control to pulse your qubit and then pulse signals to the cavity and signals to the drum. And the idea is you can overcome this dynamic range incompatibility using time domain control. The con is you have to use the strong coupling regime. And in the time it takes to do these pulses, well, you lose a lot of your beautiful quantum state just because of losses in the system. Other work you can do is you can use a qubit as your kind of nonlinear source, and you can couple it through circulators or outcoupled fields and swap single photons or superpositions of single photons to drums. Here it's great, but again, the con is you suffer the loss of intermediate things. You have to do your pump cancellation, you have circulators in between. What's nice is this only requires quantum cooperativity bigger than 1, but still, ideally, we'd like to do better. So the thing we're pursuing, I've told you about microwave circuits. I've told you how great optical circuits. What we're thinking about now is working in the intermediate regime, somewhere where we can take the best of both worlds, have access to low temperature experiments in the lumped element regime, but with higher energy photons. And that's why we're pursuing millimeter wave optomechanics. Now, by millimeter wave, what you should have in mind are tens or hundreds of gigahertz. Again, there's work going on, many groups in the field. In optomechanics, Amir Sfainahini's group is doing some work there. I also want to point out seminal work by the Harosh group, the definition of many beautiful demonstrations in quantum optics. The photons in those experiments were actually at 51 gigahertz. And so we're pushing towards technology in similar regimes. And again, from a practical standpoint, this is becoming cheaper and easier because this is precisely what 5G technology is. I also want to point out your superconductors are still superconducting, so you can still use your beautiful aluminum if you stay below 80 gigahertz or niobium if you stay below 700 gigahertz. And that you get to operate with these photons of much higher energy that don't have to be as low a temperature. And the whole thing we're after is pushing to higher frequencies, give our higher vacuum coupling rates. Now, the idea, as I said, even though we linearize around our strong pump, what is the idea is if we can get our G naught so big that our quantum cooperativity, the vacuum level is already of order 1, what that means is we can cool to the ground state with maybe 1 or a couple photons. And that's our goals that we'll have. In practice, what we can do is take our simple devices that look like this, optimize everything we know how, take our drums and make them thinner, make them suspended, make them higher Q, and take our inductor and make it smaller so the cavity frequency now moves up by a factor of 5. Together, what we're excited about is we can win a factor of 10 or more in our G naughts, maybe a factor of 1,000 in our quantum cooperativity. And this is the thing that we really believe will give us access to truly quantum regime control. Use the full power of our quantum circuits. Just as one last highlight, some of the other things we work on at NIST, we collaborate with Conrad Lehnert and Cindy Riegel over at Gilla. We're working towards ideas of quantum networking. And these are hybrid optomechanical systems where you can really think about trying to get delicate quantum information out of a dill fridge onto an optical carrier, sent across the street and perhaps down into another dill fridge. These are the ideas of quantum networking that many people in the world are pursuing. Just again, this is more of an advertisement of things we're thinking about, and we play some small part. So with that, I think I should wrap up to leave time for questions. I just want to very quickly point out the work that was done here. All of the entanglement experiments were the blood, sweat, and tears of my former postdoc, Shlomi Kotler, who now has his own group at the Hebrew University. I highly encourage you to reach out with him, collaborate with him as one of your new European colleagues, and Brad Hauer is a more recent postdoc who's pioneering the millimeter wave devices. So with that, I will stop and thank you for your time.
Thank you very much, John. That was really fascinating. So to remind the audience, you should be able to post questions in the chat, and I should be able to see them, although I don't see any yet. Oh, actually, no, there is one already from Sophia. Great. Do you want to ask it yourself, Sophia?
Yeah, sure. Thank you so much for the talk. That was really clear and really fascinating work. So I was wondering, as you talked a bit about encoding qubit states into the continuous variable oscillators, I've seen some ideas floating around that eventually you could use error correction essentially to prolong the coherence times of the mechanical systems, which would then be useful for metrology. And I was wondering if for example, that is a direction that you're looking more into, because It sounded like you're interested in sensing, but not that was immediately on the horizon.
The answer is yes, of course, these are things we are deeply interested in. Part of what I want to make sure I don't gloss over is the mechanics, despite all the things we have done, are still very nascent at that same level of doing the very clean quantum optics. So again, they're proof of principle experiments of swapping single phonons into the mechanical oscillators and measuring that it was something like a Fox state, but doing that with higher fidelity, I think, is the first thing that people are pushing toward. If you can do it, the idea is then, yes, encoding much more complex states or higher states allow you to do things like error correction, again, taking advantage of the larger Hilbert space of the linear harmonic oscillator.
Okay, thank you.
We have a question from James as well.
Hi, thanks for the great talk. I got a couple of questions actually. So one of them was, how do you choose which modes to entangle? Is it mechanical modes? Is it obvious? Is it just the fundamental is always the best one, or is there anything in there?
Generally, we choose which mechanical mode we intend to look at or couple too strong with by where we put the bottom plate of our capacitor. So here, if you look in this picture, I'm still sharing, you can see the bottom plate of this capacitor is just over this left half of the drum. And that means, well, we couple fairly well to the mode that vibrates over top of that. And other modes that are vibrating other ways cancel out by symmetry. So these were designed to particularly enhance the 1-1 mode in this direction and the 1-1 mode in this direction. And again, part of that was just to be unambiguous about which mode was which. We tend to use either the fundamental or maybe one of the low order harmonics. And again, that's just to really optimize our coupling rate. As you go to the very higher order modes, we can definitely see them. They're harder to couple to quite as strongly.
Mm-hmm. And then my second question is incredibly naive. So, seeing these beautiful talks over the years, I don't know anything about nanofabrication. And it doesn't, to me, look like the resonators have changed that much, but I'm sure there are. So what kind of technology has been really important to make these mechanical resonators better?
Let's see. First of all, I'll say you're not wrong. And part of it was, our first devices worked way better than we thought we should have. We got a bit lucky. What is amazing and the hard part is reproducibly getting this very close gap separation. Every force in the universe wants to make the drum collapse, whether it's van der Waals or Casimir or stupid patch potentials. And even worse, at room temperature, your plate separation is very different. You then put it in a dilution refrigerator and differential thermal contractions actually pull the drum's plates closer, which is great until it isn't. And so a lot of what we've been doing is playing this game of chicken to see how close we can get these plates separated and still have a viable, nice thing at low temperatures. That's been a lot of our technology. And then other things we've been pushing to is, again, just building up in complexity. Instead of 1 drum, 2 drums or 3 drums, instead of 1 cavity, 2 cavity or 3 cavity, but it's still very much at the early stages.
Great, thank you.
Thanks. Sugato has a couple of questions too.
Hi. Very, very, very interesting talk. So I'm interested in this single photon nonlinearity regime that you were talking about towards the end to improve and get to the single photon nonlinearity regime, strong coupling. So you say that with millimeter wave photons, you can go up to this kilohertz. Right. So what is the decay? So I'm interested in the regime when this will exceed the cavity decay rate. Is it possible to get those millimeter photon cavities with less than kilohertz decay?
Yes and no. So certainly people have demonstrated superconducting millimeter cavities with decay rates less than kilohertz. In fact, in those Hirosh experiments, it was their Q was 10 to the 10, or their finesse was 10 to the 10. It's unbelievably narrow. You're talking about less than 100 hertz. Unfortunately, with these vacuum gap capacitors, what you suffer from is any surface oxides give you a loss tangent. And so in practice, our cavities tend to have line widths of maybe 10 kilohertz at 10 gigahertz. Rough scale, they can be better or worse. Surface preparation can make that a little bit better. We don't know what our devices are going to be at the millimeter wave. We're hoping it's going to be on that 10 kilohertz-ish scale. So maybe we're not going to be fully in a blockaded regime, but we're going to be in a very interesting regime where we can start to see the first signs and signatures of the single photon nonlinearities.
Okay, thanks very much. That's interesting.
Sure.
And another question, is a separate question, is that you have three harmonic oscillator modes interacting in Gaussian way, essentially, right? So is there a chance of, I don't know whether that will be that novel, but whether a teleportation experiment you can in principle do, right, using these three modes, like you entangle two and try to teleport one?
That's right. Teleportation is definitely things we're thinking about. Again, it's one of the most interesting things you can do with beautiful Gaussian resources. And so the ideas of either teleporting from one drum to another or from one drum to a cavity, these are all things we're actively thinking about. And again, you could do it in between a single circuit on a chip or connect to other chips or other cavities to actually do more kind of distant teleportation. So absolutely.
Okay, thank you. Thank you.
Thank you. I'm going to go slightly out of order now because I think Peter's question relates to what you've just been talking about, John. So Peter asks, what are the technical difficulties with moving to much higher frequencies, hundreds or 1,000 gigahertz?
Yes. So the thing I want to convey is mostly it's underexplored. There's not a lot of quantum technology there. The exception, I would say, is there's a lot of mature things in radio astronomy. This kind of millimeter to terahertz regime is where a lot of the interesting radio astronomy, and actually that was my PhD, was making a millimeter wave photon detector out of superconducting circuits. Now, the idea that I just told you, you can use superconductors as a detector, shows you that photon energies there could be really big compared to superconductors. So if you're not careful, it can break your superconductivity. If you work at the right regime, again, what you're most excited about is you get the higher energies with very little of the cons. But the cons are, what you worry about is instead of having the best of both worlds between microwave and optical, is you get the worst of both worlds. Your wavelength is kind of big, but not that small. Your transmission lines are all lossy. You can do quasi-optics, but it's large. And I would say these are all the things we're excited about tackling. So our architecture, for example, is we've wired our Dilfridge with rectangular waveguide. You can make Josephson parametric amplifiers at these frequencies. I think a lot of that hasn't really been pushed on, but we're well poised to push on. And you can buy commercial hemped amplifiers and mixers, again, as commercial 5G technology that's also been used in radio astronomy. So I think the pieces are there to look around and play and seeing what all the pros and cons are. I think that's an active area of research, not just in optomechanics, but in a lot of quantum technology.
Fascinating. Thank you. Okay, Michael has a question as well.
Thanks, Edward. Great talk, John. Really beautiful results. Congratulations again. My question has been touched on by Peter already. So I'm really interested in these millimeter waves that you described today. That sounds really exciting. And I wanted to hear whether you thought it's possible to also marry superconducting qubit technology at that high frequency as well with millimeter wave optomechanics.
That's exactly in our plans, is to, again, also try to scale our transmon qubits and our circuit QED, working in those same frequency regimes. Again, if you start off as moderately ambitious of moving from 10 to 30 gigahertz, I think I'm cautiously optimistic. If you really try to go up to hundreds or thousands of gigahertz, then you might have to use different superconductors or totally different technology, which I'm open to, but is less straightforward. So our initial things are staying below kind of 40 gigahertz, where we're going to use our same aluminum and we're going to start to explore. But that's exactly the idea. Make your transmons there, see how coherent they are, but at the very least, they're beautiful number resolved single photon detectors if you want, or nonlinear Fock state single photon sources.
Okay, thanks. All the best with that path. Sounds really exciting.
Good. Okay, thank you. We are 5 minutes past the hour, so that probably means we should stop. So let us applaud John again for a fantastic talk. So take that as a round of applause, please. Do Modessa or Sophia want to say anything now before we finish?
Yeah, just a quick reminder for everyone, which is that we'll have our next seminar next week, and we'll have 3 great talks from ECRs. So please do join us for that. And then once again, thank you for John for a great and enlightening talk, and Edward for chairing the session today. Other than that, have a great week, and we'll hopefully see you next week. Sorry, just bear with me, just shutting the YouTube.